In this video, we'll explore the capabilities of the BDB platform and see how it made implementation of the Smart City POC easy. We've chosen the Smart City use case for this walkthrough because it uniquely brings together IT, OT, and ET data, enterprise systems, operational field devices, and engineering telemetry, all within one solution, making it a strong representative example of what any data-driven organization needs to solve for. Using the BDB platform, we were able to develop and deploy the Smart City Data Platform in a very short turnaround time. This is the overview of the architecture of the solution. Going forward in this video, we'll see this architecture in action, along with the various modules and features of the BDB platform in play, whether it's connecting to different sources, doing complex transformations, or enabling the consumption layer to get data on a real-time basis. We'll also see how the pre-built connectors or components made deployment and orchestration easy, with little to no headache of building everything from scratch. So let's explore together. Next, let's move on to data sources and ingestion pipelines. Here is the BDB data pipeline module under data engineering. We can quickly create a pipeline by providing a name, description, and resources. Within the pipeline canvas on the right side, we have various components: readers, writers, producers, consumers, transformation, ML, alerts, etc. These are out-of-the-box, pre-built components that the platform offers, along with the capability to build and deploy custom components that can be utilized within the environment. BDB offers a rich library of pre-built components to connect with a wide range of data sources and targets. These include DB reader components for JDBC and SQL to ingest data from relational databases, DB writer components to write processed data back to databases, MQTT consumer components for IoT data ingestion, Kafka consumer components for receiving real-time data, and Kafka producer components for publishing data to Kafka topics. BDB also supports real-time integration through WebSocket and Event Grid, along with REST API components for connecting to external applications and services. Next, it's a simple drag-and-drop functionality. Let's drag MQTT and configure the basic and meta information. It's a real-time component, so there's no option for batch or schedule. We can see it's a Docker-based deployment container. In the meta information, we add configuration details like host, username, and authentication type. Since we're configuring the AWS-managed MQTT client, we choose PEM or PPK-based authentication. This file path points to the secrets configured by admin or DevOps in the admin configuration. We choose the other details, validate the connection, and it's successfully validated. Now we add an event. Each component in the pipeline communicates with the others via Kafka events. We can choose the duration of data retention, the number of partitions, and the output. We can also mark this event as a failover event, and map it with other events for a shared Kafka event, which we'll see further in the solution flow. Then we choose another component, like transformation or writer, which will consume this event data. In the NeoCity example, this is exactly how we bring in real field data. The MQTT consumer connects to sensor topics streaming pressure, flow, and vibration readings from the water network and pump equipment, while a Modbus client reads equipment-level telemetry. As this data lands, it flows into the very first layer of the platform's medallion architecture, the bronze layer, where raw sensor readings are captured as is, ahead of the transformation and enrichment we'll see later. Next, let's move on to target storage and tables. Before we look at the actual solution implementation flow, let's explore how we can use the platform to create a DB and tables on the BDB Lakehouse, which is built on top of AWS S3 plus Apache Hudi with a Hive metastore. This is where we set up the bronze layer tables introduced in the previous chapter, along with the silver layer tables the data will progress to. We can access the Lakehouse under Data Center. Note that the complete configuration is already done by DevOps in this admin section, so it's a simple step with no deployment complexities. Now we create a new schema, provide the details, and save, then create the database. Next, we create a table, we get various options to create a table, such as DDL, a sandbox file, or manually via a defined template. We'll create it via DDL. Note that here we define only a few basic hoodie processing properties, and all other configuration and properties are handled automatically. Once the table is created, it'll be listed here. Similarly, we can see the DB and tables created for the solution, along with the complete metadata for each table, and we can set up data quality rules on top of it, as well as manage access level control and privileges. Similarly, in the data pipeline, we can create a table on the fly by defining DDL in the DB writer component for any RDBMS driver, like PostgreSQL, Redshift, etc. Now that we've covered the setup procedure, let's look at the Smart City overall flow. Next, we'll explore the solution pipeline and job flow. In the Smart City solution, we're fetching data via the Modbus and MQTT protocols. First, MQTT IoT sensor readings. Here we're utilizing pre-built components, with no code required for configuration. We're reading data from 22 AWS-managed MQTT topics, and we can see the data being consumed and sent to the shared Kafka event in real time. Next, we're reading sensor data via the Modbus client. This is a custom-built component, also producing real-time data to the shared Kafka event. Now, both the MQTT and Modbus client data are processed in a common processing data pipeline. First, the data comes into the shared Kafka event on a real-time basis. Next, the enrichment component enriches the streaming sensor data. Any failed records are sent to a failover event. Next, the transformation and enrichment component enriches and cleans the streaming sensor data, for example, mapping a raw vibration reading from a pump sensor to its asset and profile context, while an inline data quality check validates units and expected ranges. Any records that fail these checks are routed to a failover event for review. This enriched data is then streamed live to the application via WebSocket, and in parallel, the anomaly event captures anomalies based on sensor threshold rule profiles. Finally, the data gets stored in PostgreSQL using the DB writer. In parallel, the same raw sensor stream data is stored in the BDB lakehouse. First the partitioning is created, then the data is written using the lakehouse write component. We can tweak the configuration of each component and enable autoscaling, increasing instances and memory so that, based on the data load, it can spin up additional compute and memory. Now we have PySpark jobs. First, an anomaly detection job based on heuristic and statistical rules, scheduled to run every 15 minutes. The next PySpark job processes data from the Lakehouse Bronze Layer DB to the Silver Layer DB, running on an hourly batch. The complete code is written in data science module notebooks, and the complete code is registered, and the job is deployed, whether in Python, PySpark, etc., in just a few steps. Next, we'll explore the semantic business objects. Data catalog, on top of the data connectors, defines governed semantic objects in the ontology tab for the Smart City use case, such as sensors, assets, issues, and events. Each object includes complete metric definitions, dimensions, measures, and attributes, while the semantic service manages calculation rules and actions powered by database logic or Lambda-type microfunctions, which are then consumed by the Smart City Twin application. Next, let's move on to the governance and data quality. BDB provides a centralized data catalog that serves as a single place to discover, manage, and govern all platform assets. This includes tables, datasets, data connectors, pipelines, jobs, data science notebooks, and many other assets across the BDB platform. Let's open the data connector section. Here, we can see all the connectors we've worked with throughout the demo, including our bronze and silver data lake connectors, as well as relational database sources like the Smart City POC connector. I'll open the Smart City POC connector. Inside the connector, all available tables are listed. Let's select one of them. Let's select one of them, for example, the sensor table, which holds every pressure, flow, vibration, and occupancy sensor across NeoCity, or the IoT sensor readings table in the bronze layer, which stores the raw vibration and pressure readings streaming in from the pumps and valves we saw earlier in the ingestion flow. For this table, we can explore its complete metadata, including the schema and structure. We can also access the data quality dashboard, which provides visibility into the latest execution, historical runs, pass or fail statistics, and any data quality issues detected over time. Below that, we can view all the data quality rules configured for this asset, and from here, we can create or manage additional rules as needed. If we navigate back to the connector level, we can also explore the associated ontologies, which provide the semantic layer we discussed earlier, along with the corresponding taxonomies used for business classification. The catalog also maintains a complete audit history, allowing us to track who made changes, what was modified, and when those changes occurred. In addition, every asset contains rich governance metadata, including its steward, owner, lifecycle status, last access timestamp, and business tags, making asset ownership and governance completely transparent. Overall, the BDB data catalog provides comprehensive asset discovery, governance, lineage, metadata management, and integrated data quality capabilities from a single, centralized interface. Next, we'll explore data asset lifecycle management, versioning, Git integration, and data as API. BDB provides built-in capabilities to manage the lifecycle of data assets, enabling teams to track ownership, monitor activity, control access, manage changes, and promote assets across environments with confidence. Using a pipeline or job as an example, users can view important lifecycle information such as who created the asset, when it was created, when it was last updated, and its most recent activity. This provides clear visibility into the asset's ownership, current status, and operational history. The platform also supports usage monitoring, helping teams understand how frequently an asset is executed or consumed. User permissions and access controls can be configured to ensure that only authorized users can view, edit, execute, or manage the asset. BDB also provides built-in support for version control and Git integration. Users can push and pull assets from Git repositories, making it easy to integrate with existing enterprise development and deployment workflows. Versioning is supported across multiple asset types, including data services, data pipelines, jobs, and DS Lab notebooks. Every change can be tracked, allowing teams to maintain version history, collaborate effectively, and roll back to previous versions whenever required. In addition to version control, BDB supports Git-based asset promotion and migration across environments. Using Git as the deployment mechanism, organizations can seamlessly promote assets from development to testing and then to production, while maintaining consistency, traceability, and governance throughout the lifecycle. BDB also enables users to expose governed data assets as APIs. Users can navigate to the data center, select the required dataset, and choose the data as API option. They can then configure the service name, description, category, parameters, record limits, and response structure before publishing the service. Once the data API is created, it can be registered and governed through the admin module using API client registration. Administrators can define the consuming application, configure request limits, select the API type, and assign the required entitled services. This ensures that only authorized applications can securely access the published data. After saving the registration, the platform generates a unique client ID and client secret key for the consuming application. These credentials are used to authenticate API requests and should be stored securely. The platform also provides a documentation link for the entitled service. By opening this link, users can view the complete API specification, including the service endpoint, request method, required headers, authentication details, request parameters, and supported response codes. The documentation also displays sample success and error responses, helping development teams understand how to invoke the API and handle different outcomes. The generated credentials can then be used by authorized applications to securely consume the published data API. Overall, BDB combines asset lifecycle visibility, usage monitoring, access management, Git-based version control, environment promotion, and governed data as API capabilities to provide secure, controlled, and consistent management of enterprise data assets. Next, we'll explore monitoring and observability. BDB provides a comprehensive monitoring and observability framework out of the box, enabling operations teams to proactively monitor platform health, identify issues, and ensure reliable data operations. The centralized monitoring dashboard provides real-time visibility into critical platform events, including failed workloads, processing delays, offline connectors, cluster health, Kafka monitoring, infrastructure health, and database performance. From a single interface, users can monitor all active compute workloads, tenant services, and execution services running across the platform. Detailed logs are available for every service, allowing operators to quickly investigate failures, identify root causes, and take proactive corrective actions before they impact downstream systems. The platform also includes an integrated alerting framework, ensuring that operational teams are immediately notified of critical events and can respond proactively to maintain service reliability. In addition to platform-level monitoring, BDB provides pipeline-level observability. Within every data pipeline or job, users can monitor execution status, track runtime metrics, and leverage built-in failover capabilities to quickly identify and recover from processing failures. The monitoring dashboards expose detailed operational metrics for every pipeline component, including compute utilization, memory consumption, throughput, data processed, failed records, and overall execution performance. For deeper troubleshooting, users can access component-level system logs, providing complete execution details generated by each processing stage. This significantly simplifies debugging and root cause analysis. While BDB delivers a rich, built-in monitoring experience, it also integrates seamlessly with enterprise observability tools such as Grafana, Kibana, and the Kubernetes dashboard, allowing organizations to leverage their existing monitoring ecosystem alongside BDB's native capabilities. Overall, BDB delivers end-to-end visibility across the platform, from infrastructure and services to individual data pipelines, helping organizations maintain high availability, operational efficiency, and reliable data processing. Next, move on platform deployment scenarios. BDB is a cloud-agnostic platform that can be deployed on any major cloud provider, including AWS, Microsoft Azure, and Google Cloud Platform, GCP, as well as in on-premises environments. This gives organizations the flexibility to choose the deployment model that best fits their infrastructure, security, and business requirements, without being tied to a specific cloud provider. With its comprehensive capabilities, from data integration and governance to monitoring, cataloging, and application development, BDB enabled us to rapidly build and deploy the Smart City Digital Twin Solution, Smart City Data Platform Solution, spanning IT, OT, and ET data end-to-end. The platform's pre-built connectors, centralized governance, and rich monitoring capabilities significantly accelerated implementation, allowing us to deliver the complete solution in less than a week. Thank you for your time. We hope this demonstration has provided a clear overview of how BDB enables organizations to build scalable, governed, and intelligent data solutions with speed and confidence.